Representation Theory of Finite Groups, Lecture 13, Permutation Modules. So this lecture starts the third part of the course, and the aim of this part is to describe the basics of the representation theory of symmetric groups. We start with some general remarks about the symmetric group. First of all, we will use the convention that the symmetric group for the empty set is just the group with one element. Let n be a positive integer. Denote by n underlined the set consisting of all positive integers between 1 and n. Consider the symmetric group as n of all bijections from n underlined to itself. The group operation here is composition of functions, and the identity element is the identity function. Each element alpha of Sn can be described using the two-line notation. So here we treat alpha as a function, and in the first line we list the arguments, so the elements from 1 to n, and in the second line we list the values of alpha on these elements. Alternatively, one can also use the one-line notation if one agrees that the arguments in the first line are just listed increasingly with respect to the natural order. There is a third way to describe elements in the symmetric group, and this is using the cycle notation, alternatively via the action graph of the element. So each element sigma in Sn can be described using its action graph. So here's a definition of the action graph by example. Let sigma be the permutation which sends 1 to 3, 2 to 6, 3 to 5, 4 to 4, 5 to 2, 6 to 1, 7 to 7, 8 to 9, and 9 to 8. Then here is the action graph of this permutation. So 1 is sent to 3 is sent to 5, 5 is sent to 2, 2 is sent to 6, and 6 is sent back to 1, and so on. Since sigma is a bijection, its action graph is a union of disjoint cycles. And then we can write the cycle notation for sigma. So we have the cycle 1 goes to 3, then to 5, to 2, to 6, and back to 1. So here is this cycle. Then we have the cycle 8 goes to 9 and back to 8, 8, 9, and then 4 goes to itself, and 7 goes to itself. And the cycles of length 1 can be dropped. So the typical short version of the cycle notation for sigma is the product of the cycles 1, 3, 5 to 6, and 8, 9. Note that different cycles in the cycle notation commute. And also each cycle is defined up to a cyclic permutation of its elements. So in particular, the notation for the cycle 1, 2, 3, this describes the same cycle as described by the notation 2, 3, 1. The cycle notation allows us to define the cycle type for a permutation. For this, we just write the lengths of the cycles in the decreasing order and with multiplicities. And we also include all cycles of length 1 here. So if we do that, we obtain the cycle type of sigma. So for example, our previous permutation on 9 elements, sigma, which was a product of 4 cycles, one of length 5, one of length 2, and 2 of length 1, has cycle type 5, 2, 1, 1. Note that the entries of the cycle type for sigma add up to n. And we have already seen the following proposition. For 2 elements in Sn, the following assertions are equivalent. These 2 elements are conjugate. The action graphs of these 2 elements are isomorphic. And the cycle types of these 2 elements coincide. Recall our general representation theory for finite groups. In particular, we know that the conjugacy classes of the group index the simple modules over this group. From this proposition, it follows that the simple modules over the symmetric group are indexed by the cycle types which appear in this symmetric group. So it makes sense to axiomatize the structure which is formed by the cycle types. And the structure is known as partitions. So what is a partition? A partition of n is a vector lambda with entries lambda 1, lambda 2, and so on, lambda k, such that all these entries are positive integers. They decrease, so lambda 1 is greater than or equal to than lambda 2, that is greater than or equal to than lambda 3, and so on, and they add up to n. So this is the usual notation to say that lambda is a partition of n. Here are some examples. If n is equal to 1, we have only one partition, which is just 1. There are two partitions of 2, the partition 2 and the partition 1, 1. And there are three partitions of 3, the partition 3, the partition 2, 1, and the partition 1, 1, 1. So here is a little bit odd but commonly used notation. So if we have a partition and we have a repetition of some part several times, so if the part A is repeated exactly b times in the partition, one usually denotes it by a to the power b. So for example, the partition 2, 2, 1, 1, 1, this is a partition of 7, is usually denoted 2 to the power 2, 1 to the power 3. This is a slightly misleading notation, but it is commonly used. Observe that the cycle type of each permutation in Sn is a partition of n, and any partition of n is the cycle type of some permutation in Sn. In particular, there is a bijection between partitions of n and conjugacy classes in Sn. Now, from our general theory, we know that there is a bijection between partitions of n and isomorphism classes of simple Sn modules. So the aim of this part of the course is to construct all simple Sn modules using intrinsic combinatorics of partitions. And for this, we need to develop several combinatorial tools related to partitions. So the first combinatorial gadget which we are going to talk about is the Young diagrams. So a Young diagram, also sometimes known as a Ferrer's diagram, is a finite collection of boxes, also called cells, which are arranged in a left justified rows with the row lengths in weakly decreasing order. So here are some examples. So we have here the collection with 4 boxes in the first row, 3 boxes in the second row, 3 boxes in the third row, then 2 boxes, 2 boxes, and 1 box. So here is another Young diagram, and here is another Young diagram. There is, of course, an obvious bijection between partitions of n and Young diagrams with exactly n boxes. So the Young diagram of a partition lambda contains lambda 1 boxes in the first row, lambda 2 boxes in the second row, and so on. And it is usually convenient to identify partitions with the corresponding Young diagrams. So for example, so we have seen that there is only one partition of 1, which is 1. So there is only one diagram with one box, just a box. There are 2 partitions of 2, so we have 2 corresponding Young diagrams. The Young diagram with 2 boxes in the first row, and that's it, or the Young diagram with 1 box in row 1 and 1 box in row 2. So for 3 boxes, we have 3 Young diagrams. So the first diagram has 3 boxes in the first row. The second diagram has 2 boxes in the first row and 1 box in the second row. And the third diagram has 1 box in rows 1, 2, and 3. The next gadget which we need is the notion of a Young subgroup of Sn. Let us fix a partition lambda of n. Denote by S lambda the set of all elements sigma in Sn such that sigma permutes the elements between 1 and lambda 1. So if you take an element between 1 and lambda 1 and apply sigma, you end up in the same set of elements. Then sigma permutes the elements from lambda 1 plus 1 and so on until lambda 1 plus lambda 2. So if you take any element from this set and apply sigma, you end up in this set, and so on. It is very easy to see from the definitions that S lambda is a subgroup of Sn. And this S lambda is called the Young subgroup of Sn corresponding to lambda. And also directly from the definition, it is easy to see that S lambda is isomorphic to the direct product of the symmetric group S lambda 1. So this corresponds to permutation of elements between 1 and lambda 1. Then the symmetric group S lambda 2. So we have lambda 2 elements in the second set, lambda 1 plus 1 and so on, lambda 1 plus lambda 2, and we can permute them as we like, and so on. So for example, the subgroup S2, of S4 consists exactly of the following elements. We have the identity, we can permute 1 and 2, so we have the transposition 1, 2. We can permute 3 and 4, so we have the transpositions 3 and 4, and we have the product of 1, 2, and 3, 4. And this Young subgroup is isomorphic to S2 times S2. So our next notion is the notion of a Young tableau. Fix a partition lambda of n. A Young tableau of shape lambda is a filling of the boxes of the Young diagram of lambda with elements from our set n underlined. So each box should be filled with one element, and each element from n underlined can only be used once. So tableau is a French word, and the plural is also tableau, written with x at the end. So we denote by yt sub lambda the set of all Young tableaux of shape lambda. And directly from the definition, it is obvious that the set yt lambda contains exactly n factorial elements. So here's an example of all elements in yt 2, 1. So we have the Young diagram with two boxes in the first row and one box in the second row, and we should write elements 1, 2, and 3 in these boxes. So we have 1, 2, 3, 2, 1, 3, 1, 3, 2, 3, 2, 1, 2, 3, 1, and 3, 1, 2. We have 6 elements in this set. Next, let us talk about Young tabloids. Two Young tableaux of the same shape are called row equivalent, provided that one of them can be obtained from the other one by permuting elements within each row separately. Definition: a row equivalence class of Young tableaux is called a Young tabloid. Notation: so for example, this denotes the row equivalence class of the Young tableau 1, 2, 3, 4, 5, 6. So we delete the vertical lines in the notation for the Young tableau, somehow in order to signify that now you can permute elements within each row separately. Let us denote by ytd sub lambda the set of all Young tabloids of shape lambda. So for example, the Young tabloid for 1, 2, and 3, 4 consists of the following 4 Young diagrams. So we have 1, 2, and 3, 4. We have 2, 1, and 3, 4, 1, 2, 4, 3, and 2, 1, and 4, 3. So this is a Young tabloid. It's just a set of Young tableaux which are row equivalent. So now let us use Young tableau to give an alternative model for the regular Sn module. Of course, the symmetric group Sn acts on the set of all Young tableaux of shape lambda by acting on all entries of the tableau. So for example, if you take a sigma the permutation 1 goes to 2, 2 to 3, and 3 to 1, and you try to apply sigma to the following Young tableau of shape 2, 1 with elements 1, 2, and 3, you get the Young tableau of the same shape, where now the first box should contain sigma of 1, the second sigma of 2, and the third sigma of 3. And this gives us 2, 3, and 1. So Sn acts on yt sub lambda, so we can consider the linearization of this. This is an Sn module. And the claim is that this Sn module is isomorphic to the regular Sn module. So we have just discussed that the dimensions of both this module, which we just constructed, and the regular module, both dimensions are equal to n factorial, so they agree. So if we send the identity element from the regular module to any element of any module, this extends to a homomorphism. So we can send this identity to a fixed element t in yt lambda. And this gives us a homomorphism of Sn modules. But since if we take this element t in yt lambda and apply Sn, we can get any other element in yt lambda, it follows that this homomorphism is surjective. And since the dimensions agree, it is also injective, so it is an isomorphism. Now we can define the main protagonist of today's lecture. These are the permutation modules. Similarly to the previous slide, Sn acts on the set of all Young tabloids of shape lambda. So for example, if we take the permutation which sends 1 to 2, 2 to 3, and 3 to 1, and apply it to the tabloid now, where the first row has 1 and 2, and the second row has 3, we get the tabloid where the first row is sigma of 1 and sigma of 2, and the second row is sigma of 3. So this is a tabloid 2, 3 in the first row and 1 in the second row. And again, we can consider the linearization of this action. This is an Sn module, which we denote by m upper lambda. So curly m and upper lambda. This now heavily depends on the shape lambda. Terminology: this module, curly m upper lambda, is called the permutation module corresponding to our partition lambda. We will often use the following notation, so we denote by lambda factorial the product of all parts in lambda, the factorials of the corresponding parts. And then we can observe that the dimension of the permutation module, of course, it is equal to the cardinality of the set of all Young tabloids of the shape lambda. This is equal to n factorial divided by lambda factorial. This is because we have row equivalence classes. So we take n factorial Young tableaux, and then we can permute elements in the first row independently. This gives us lambda 1 factorial. We can permute the elements in the second row independently. This gives us lambda 2 factorial, and so on. Consequently, we get that the number of Young tabloids of the shape lambda is equal to n factorial divided by lambda factorial. So here is an explicit example. Consider the partition 2, 1 of 3. Then we have exactly 3 Young tabloids of this shape. So the Young tabloid where you have 1 and 2 in the first row and 3 in the second row, the Young tabloid where we have 1 and 3 in the first row and 2 in the second row, and the Young tabloid where we have 2 and 3 in the first row and 1 in the second row. The action of the generators 1, 2, and 2, 3 of S3 in this basis of the permutation module is then given by the following matrices. So the element 1, 2 doesn't do anything to the first tabloid because it just permutes elements in the first row, but for tabloid this doesn't matter. So it sends the first basis element to the first basis element. 1, 2 sends 2 to 1, so it sends the second basis element to the third basis element and back. So the second column will be 0, 0, 1, and then 0, 1, 0. So this is the action of 1, 2 in this basis. The action of 2, 3. So 2, 3 swaps the first and the second element and keeps the last one. So the matrix will be column-wise 0, 1, 0, 1, 0, 0, 0, 0, 1. The general notation for any Young tableau T, we denote the corresponding tabloid T in the set brackets. So this is now the row equivalence class of T, which is an element of YTD sub lambda. So in other words, we denote by the set brackets the projection map from the set of all Young tableaus of shape lambda to the set of all Young tabloids of shape lambda. Here are some more general examples. Consider the partition of n, which consists only of one part, n. Then the corresponding Young diagram has only one row. In particular, we have only one tabloid of this shape, because all elements are in the first row, so all Young tableaus of this shape are equivalent. If we apply any element sigma to this tabloid, we permute elements in the rows. This doesn't change the tabloid, so we get our tabloid back. In particular, the permutation module, which corresponds to this partition n, is just the trivial Sn module. Example 2, let us consider the opposite case, the other extreme. Consider the partition lambda given by 1, 1, 1, 1, 1. So it has n parts, all equal to 1. Then different Young tableaus cannot be row equivalent because all rows contain exactly one element. In other words, the set of Young tableaus coincides with the set of Young tabloids. So the permutation module is just the linearization of the module on Young tableaus, and we have seen that this is exactly the regular module over Sn. So one extreme gives us the trivial module, the other extreme gives us the regular module. So here is a less trivial example. Consider the permutation lambda consisting of two parts, n minus 1 and 1. Then we have exactly n Young tabloids of this shape. So as soon as we choose an element from 1 to n into the second row, all the rest should be placed in the first row, and it doesn't matter how you place them because it's a row equivalence class. So let us denote the tabloid where I is placed in the second row by I, by the special font I. Then, of course, if you apply sigma to the special font I, you get the special font J. So if J is simply sigma of I. In other words, this permutation module is isomorphic to the natural Sn module. So it has a basis given by numbers from 1 to n, and the elements of Sn act on this basis by simply acting on the numbers. So this permutation module is the natural Sn module. So now let us describe some algebraic properties of permutation modules, and the first one is cyclicity. Definition: a module M over an algebra A is called cyclic, provided that it is generated by one element. In other words, there is an element V in this module M, this should be M, such that A applied to V is equal to the whole of M. Proposition: the permutation module M lambda is cyclic as an Sn module. In order to prove this, we show that the permutation module is generated by any Young tabloid. So let us fix some Young tabloid T in set brackets. This is an element from YTD sub lambda. Let n be a submodule of M lambda containing this T. Then, of course, n must contain sigma of t for any sigma in Sn. But applying Sn to any Young tabloid of shape lambda, we can obtain all Young tabloids of shape lambda. This means that our submodule n must contain YTD sub lambda. But this set is a basis of M lambda, which implies that n is actually equal to the whole permutation module. So this proves our proposition. Now let us give a general alternative description for permutation modules. Theorem: for any partition lambda of n, the following modules are isomorphic. Module 1 is the permutation module M lambda. Module 2 is the induced module induction from S lambda to Sn of the trivial S lambda module. And module 3 is the coset module for Sn, where S lambda acts on the right. An immediate observation: all these three modules have dimension n factorial divided by lambda factorial, which is also equal to the index of the Young subgroup S lambda in the whole group Sn. Okay, so let us prove the first isomorphism. So let us construct an isomorphism between the induced module from S lambda to Sn, so the induced trivial module, to the permutation module M lambda. Consider a Young diagram of shape lambda, and let us fill its boxes with the numbers 1, 2, and so on up to n, in the order left to right and top to bottom. So let us denote the Young tableau which we obtain in this way by t. So in other words, the first row of t is 1, 2, 3, and so on, lambda 1. The second row of t is lambda 1 plus 1, lambda 1 plus 2, and so on, lambda 1 plus lambda 2, and so on. And then let us consider the tabloid corresponding to t. And then from the definition, it follows that if you apply to this tabloid an element of S lambda, you will get this tabloid back. Because S lambda permutes by definition the elements in the first row, so it doesn't change the tabloid. It permutes the element of the second row, so it doesn't change the tabloid, and so on. In particular, the linear span of this tabloid, so the one-dimensional subspace which is generated by it, it is an S lambda submodule of the permutation module, and it is isomorphic to the trivial S lambda module. In other words, we have a non-zero S lambda homomorphism, let's denote it by phi, from the trivial S lambda module to the restriction of the permutation module from Sn to S lambda. By adjunction, or as we called it, the Frobenius reciprocity, this S lambda homomorphism phi corresponds to a non-zero Sn homomorphism psi from the induced trivial module to M lambda. So let us choose an element V in the trivial S lambda module, which is sent by phi to our tabloid T. Then by the construction of psi of V is equal to phi of V is equal to T. Hence, for any element sigma in Sn, if we apply sigma to the element gi of V, so this is a basis element of the induced module, so this is equal to the application of sigma to the tabloid obtained by applying gi to T, because V is sent to the tabloid of T. And this is simply a tabloid of sigma applied to gi of T. But we can use any sigma in Sn, and so here inside the set brackets, we can get any Young tableau of shape lambda. And when we take the set brackets, we can get any Young tabloid of shape lambda, which means that psi is surjective because Young tabloids form a basis of the permutation module. But since the dimensions of the induced module and the permutation module coincide, it follows that the homomorphism psi is an isomorphism. And this proves that the first two modules in our list are isomorphic. So this proves that the permutation module is isomorphic to the induced module. Now, second isomorphism, similarly, one shows that the induced module is isomorphic to the coset module. So here is now a brief sketch of this proof. Consider the coset, which is just the subgroup S lambda. So this is a basis element of the coset module. Of course, sigma of S lambda is equal to S lambda for any sigma of S lambda. So the action is just the multiplication. Therefore, the coset S lambda generates a trivial S lambda submodule of the coset module. So by adjunction, this corresponds to an Sn homomorphism from the induced module to the coset module, which sends the generator V here to S lambda. But the coset module is generated by S lambda. So if you start from S lambda and multiply on the left with elements in Sn, you will get all the cosets. So this homomorphism is surjective. And again, since the dimensions coincide, it should be bijective. And this completes our proof. So here is an example. So consider the partition 2,2 of 4. Then S lambda, we have seen it. It consists of the identity, the transposition of 1 and 2, the transposition of 3 and 4, and the product 1, 2, and 3, 4. Let us fix the following representatives in Sn modulo S lambda acting on the right. So we have the identity, then we can swap 3 and 2, then we can have the cycle where 2 goes to 4 and 4 goes to 3 and 3 goes to 2. Then we have the cycle 1 goes to 2, 2 goes to 3. Then we have the cycle 1 goes to 2, 2 to 4, 4 to 3, and 3 to 1. And finally, we have the product of the transpositions 1, 3 and 2, 4. Here are the Young tabloids of shape 2, 2, which corresponds to these coset representatives. So the identity gives us the standard tabloid, 1, 2, and 3, 4. Then we can place 1 and 3 in the upper row and 2, 4 in the second row. 1, 4 in row 1, 2, 3 in row 2, 2, 3 in row 1, 1, 4 in row 2, 2, 4 in row 1, 1, 3 in row 2, 3, 4 in row 1, 1, 2 in row 2. And then the standard basis of the induced module is of the form GV, where V is the basis of the trivial module, and G is one of our 6 representatives. And the isomorphism, which we constructed in the previous theorem, it sends this element GV to the corresponding Young tabloid. So the element identity V is sent to this tabloid. So if this is G, then GV is sent to this tabloid, and so on. So this is how the theorem works in reality. Let us finish with some further problems and questions. Question 1. Denote by Pn the number of all partitions of n. Prove that the generating function for the sequence Pn is equal to the product over all I from 1 to infinity, and then 1 divided by 1 minus x to the power I. Question 2. Check with all details that for any partition lambda of n, the set S lambda which we defined is a subgroup of Sn isomorphic to the direct product of S lambda 1, S lambda 2, and so on. Question 3. Prove with all details that the number of Young tabloids of shape lambda is equal to n factorial divided by lambda factorial. Question 4. Prove that for any subgroup H of a group G, the induced trivial module from H to G is isomorphic to the coset module for G modulo H, where H acts on the right. Question 5. Compute the matrices of the action of the generators of S4 with respect to the standard basis of the permutation module corresponding to the partition 2, 2. Thank you very much, and see you next time.